Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our pointers demo. This video is part of a series of videos that are going to focus in on the ability in C to access the memory directly. I will interchangeably use the term pointers by address and by reference when I'm referring to how we're going to access a variable using its memory address or memory location. So you want to make sure that you have completed the setup of your pointers demo for this video, as well as the first video or the first snip that had the first 3 examples in it. We're going to be leveraging them as well in this video. And also that you have located a copy of the pointers o2.c snip. Once again, this is a very long file, and so I'm going to go ahead and give you the code, and basically what we're going to do is we're going to talk our way through it. So to begin with, go ahead and bring over your function signatures and add them to the list, as well as the implementations. Please note that we have an example add1 version 3 modified that is essentially derived from our earlier example add1 version 3, and also that we have helper functions in this example as well. So go ahead and copy all of the code and the comments and just simply go ahead and add it to the bottom of our file. Now, next thing we need to do is we need to go ahead and update our main to accommodate our new functions, as well as update the help. Once we're done with this, then we will jump into discussing how these functions work. So to begin with, what we want to do is we simply want to borrow one of our earlier lines of code that allowed for us to handle the different command line options or the different switches. Particularly, we want to change the version 3 now to version 3 modified, and also following along with the name of the function here, be doing the version 3 modified. And in addition, we want to handle the add1 version 4 switch, as well as calling the add1 version 4 function. We're going to additionally add one last switch, and this is what I'm going to refer to as a convenience switch, in which case what we're going to do is we're actually going to call all of our examples up to this point, and we're going to do it all at once, or rather sequentially, but we're going to do it with one command line switch. So what we're going to do here simply is to call our version 1, immediately followed by our version 2, version 3, version 3 modified, and lastly our version 4. Now this is going to quickly become a mess because there's going to be a lot of output on our command window. However, there is one particular aspect of this that we want to be able to focus on, and so it's very important that we can essentially run all of our functions serially or one after another without restarting our executable. At this point, then, the only thing that's left is to simply make some modifications to our help. I'm going to keep these very basic, and I'm going to encourage you to improve on these later. So we want to add the ability to have the version 3 modified, version 4, and then, of course, the all switch. At this point, that's essentially all the code that we're going to write for this example, so you can go ahead and build it. And if you don't have any errors, then go ahead and open your command line and cd to the directory with your executable. Now, before we get started looking at the code, I want to take just a second to describe what we're actually going to do in this example. Rather, before we take a look at the command line, I want us to take a brief look at what we're actually going to do here. And so you'll notice in our additional 2 functions, starting with the example add1 version 3 modified, that essentially I'm doing something similar to what I did in the earlier example, where I am creating a local integer variable. I'm assigning a value to it, and then I'm simply passing it to my add1 version 3. The difference this time, however, is that I am also creating another local variable that is a pointer to an integer. And the purpose for this is that we are going to store the address of our int underscore a3 in a separate variable, and then we're going to pass that variable to our add1 version 3. So for comparison's sake, what I'd like for you to do is to take a look at the earlier example, add1 version 3, and you'll note that I use the ampersand to indicate the address of int underscore a3. In the second example, I am doing essentially the same step, but I'm doing it earlier, and I'm taking the address of that integer and I'm simply placing it in another variable. And so what I'd like to do for just a second is to sort of help you understand what that's supposed to look like and how do you store a memory address. Well, first we're going to look at a single variable, our int underscore a3. It is of type integer, and we are assigning a default value to it of 0. And we can also get the memory address. In other words, we can discover where in memory this variable is located. And we did that in our earlier example, and you saw that in the table, and we're going to look at that again in just a second. And just as a little bit of added information, the size of an integer is in fact 4 bytes. And if you keep with the idea that a variable can be thought of as a box containing information, with the type, value, address, and size being some of the critical pieces that you need to know about it, then essentially it isn't too big of a jump to think of the fact that we can essentially store the address of one variable in another variable. And to understand how we do this, then imagine creating another box, and this one we call int underscore a3 underscore pointer. Now don't get too hung up on these names. I realize if anything they're rather terrible variable names, and also they include the data type, so this is probably not best practice. This is just simply to help us understand what's going on. But this second variable now is a pointer to an integer. Now, note here that it has a value that also looks like a hexadecimal value or a address in memory, but it itself has an address, okay? And the address or the location of int a3 pointer is the FEC8, or the second address that you see. And also, just by coincidence, the size of an integer pointer is in fact 4 bytes. Now, what's the relationship between these two variables? Well, it turns out the value that was stored in our int underscore a3 underscore pointer is the address of our int underscore a3. So essentially what is happening is I have the variable on the left is being used to point to the variable on the right. So if you aren't comfortable yet with this concept, I encourage you to spend some time thinking about this, and if anything, review this portion of the video until you feel comfortable moving on. This is a very, very critical portion of the remainder of our topics in pointers, and also when it comes to our more advanced data types. So back to our code, you'll see that essentially I have built in C a nice table like we did in our earlier examples that does exactly that. It simply demonstrates the value of int a3, the address of int underscore a3, the size. We then also print out the value of the pointer. Now, I didn't emphasize this in the earlier video because I didn't want to give us too much information, but you'll notice that in the printf statement, I have a %p. This is what allows for me to print out that hexadecimal value that you saw in the earlier example. Also note that I am printing out the address of the int A3 pointer. So essentially what I'm doing is I am printing out the address of the variable that is storing the address of our int underscore A3. And then lastly, of course, I'm printing out the size. And this is all done prior to adding our 1, as you'll see. But this time we are passing the address of the variable int underscore A3. So essentially we're allowed to modify our int underscore A3, and then the table just completes by showing us what we've accomplished. So without further ado, let's go ahead and jump over to the command line, and let's go ahead and run now our version 3 modified. So in this case, what I want to do is I want to follow our exe name with the name of the function. So in this case, it's going to be example underscore add underscore 1 v3 modified. And you'll see that we have this nice table just like we did in our earlier example. And let's take just a second to put NetBeans and our console up next to each other. And you'll see here that we, in fact, start off with an initial value for A3 of 0. The address or the location of our int A3 is at FECC. The int A3 pointer stores the value of that location. And then we have the address of our int A3 pointer essentially comes sequentially after our A3 int A3 variable. Now, the location in memory relative to each other is not important. You'll actually discover that that depends on the order in which you have created the variables or declared the variables. So don't worry too much about the fact that essentially our int3, or the relationship rather in memory between our int underscore A3 and our int underscore A3 pointer, but also notice then that the size of both of them is 4. Now, we are passing to our little helper function, our add1 version 3, the value of 0, but we're doing it by reference. In other words, we're passing the memory address of our int A3. And inside the function, we once again are demonstrating that we have the same memory address for our int underscore A, as it's known inside the function, as the address of our int underscore A3, much like what we did earlier. We're adding 1 to it. And please note that we are not actually returning a value. It's very important to understand that there is no return value from this function. Rather, we are directly changing or impacting, modifying, whichever way you want to think about it, the value at a specific location in memory. And once again, to prove that, you'll see that in lines 215 and 216, I am printing out the value of our int underscore A, as well as the address. Once the function does return back to the calling function, in this case, our example add1 v3 modified, we once again complete the table by printing out the values for int underscore A3. You'll notice that there is no change in the memory address, which doesn't seem too terribly surprising. And also the value of our int underscore A3 underscore pointer, which of course also does not change. We didn't make any changes to the memory address or to the memory location. And then lastly, we have the value, or rather the address of the int underscore A3 underscore pointer. In other words, if you go back to our PowerPoint for just a second, essentially that represents the address of this second block of memory that is being used to store the address of the first. Now, what we want to do is we want to go back and we want to look at our earlier examples now in context with this example. And to do that, what I want to do is I want to run my all switch. And so this one's going to get a little bit messy because it's going to run all 5 of our demos so far. And we're not going to yet look at our version 4, but instead what I want to do is I want to look at the first 3 examples. In other words, the ones that we actually did in an earlier video, but we didn't run them one after another. We ran them as separate instances of our executable running. In other words, we went out to the command line and we reran our executable. But even in that video, if you were very careful, you probably noticed that there was a similarity in the values or the addresses of our variables. As a matter of fact, coincidentally, they are all the same. So if you notice here, our int underscore A1 from our first example is in fact FECC. The int underscore A2 is also FECC. And the int underscore A3 is FECC. Well, now how is that possible? Well, it turns out that essentially that local space that is used for the variables in the functions, those locally scoped variables, gets recycled. So essentially, once my example add 1 version 1 was finished running, the memory was given back to the system to be used later. That is what allowed for us to create this variable and at the location FECC. Once this function was completed, then that memory could be reused, and it was in fact reused by the declaration of our int underscore A2. Once that function completed running, the memory was once again reused for our int underscore A3. Now, the reason that I'm going through and emphasizing this is because I'd like for us now to take a look at our example add 1 version 4. And in our add 1 version 4, we want to ask the question, why don't we simply use pointers everywhere? You will see that we're going to use pointers and by reference variables quite a bit throughout the remainder of these videos. However, there are certain examples or certain ways in which we cannot use them. So what I'd like to do in our example add 1 version 4 is I would like for us now to do the same problem that we did earlier, utilizing our 2 variables, essentially our int A4 and our int B4. And what we're going to do is we're going to call another little helper function. The helper function this time will accept a reference to an integer or the address of an integer, and it will return a reference or a address to an integer. So essentially this would look like a great idea because basically we can modify the values and by simply accessing an address in memory. Well, let's go through what we're planning on doing here, and then we're going to take a look at the table that we have printed out in our console and see if we can understand what's going on. The first thing that I do here is I also go back and declare 2 integer pointers. In other words, 2 variables that will store a memory address of an integer. And notice how I've named them such that my int underscore A4 underscore pointer is essentially going to hold the address of my int underscore A4. Likewise for my B4. Now, I am initializing the values of my 2 integers. I am for right now going to completely leave alone the pointers. So if you recall from our earlier videos, we talked about declaring variables and initializing variables as two separate steps. If you declared a variable, but you forgot to initialize it, you would essentially treat or would consider the value in that variable as nonsense or garbage, or at the very least, unpredictable. In other words, you couldn't use it later on without initializing it or assigning a value to it with any sort of confidence of what your value is going to be. So we're going to simply initialize my two integers, but I am in fact going to do nothing at all about initializing these two variables that are pointers to integers. And you'll note here specifically in the first part of the table, I am actually going to print out the addresses of not only the integer A4, but also the value that was in the uninitialized pointer or integer pointer. In other words, we're just going to see what's currently there. We are also going to print out the address of that pointer variable that will ultimately point to our int underscore A4, and we do the same thing with our B4. And now what we want to do is we want to come over here to the table and we want to see what this looks like. And so starting with this table header here for the description of our example, add one B4, you'll see that there is my int underscore A4, which is 0, not a big surprise. FECC is the address of that variable. We also have the int underscore A4 pointer, which is going to reside at our FEC8. And then we do the same thing now with our int B4 pointer and the address of the int B4 pointer. All right, so we want to take a little bit of care to notice these addresses. And then what we're going to do is we're going to turn around and nullify both of them. Okay, and so if you take a look now at the table below this, we'll see that we have the int A4 pointer has the value of 0. So at this point, this is how we initialize a pointer. So essentially, this is the equivalent then of 0 for a pointer or 0 for an address. It essentially points to nothing. That does not change the address of the int underscore A4 underscore pointer variable. So if you think back to the PowerPoint, we didn't do anything with that left box. In other words, we didn't change where that left box was sitting in memory. We simply erased the value that was stored at and initialized it to effectively 0. And now you'll see here in the code, we are simply printing out those values. Our next step is to go ahead and assign what we want to, or the correct values, if you would, to those two pointer variables, much like we did in our V3 modified. We simply take the address of our int underscore A4 and we assign it to the variable int underscore A4 underscore pointer. Likewise, we do the same thing with our B4, and you'll see then this corresponds to the table here that starts off with the set the pointer of the address to int underscore A4. So value of int A4 doesn't change. The address of int underscore A4 doesn't change. Neither does the value of B nor the address of B. Simply the values that are stored at int A4 pointer is now FECC, and the value stored at int underscore A4 pointer, which is 0, and the int B4 pointer, the address that is stored there, is also going to be FEC4, which corresponds to the address of int underscore B4. This brings us to something that we have not yet seen. Notice that I have both the value stored at int underscore a for underscore pointer and for int underscore b for underscore pointer. So essentially what I'm doing here is I'm saying give me the actual value that is stored at this location. And this is referred to then as the redirection operator, which essentially allows for us now to get the value at that particular location in memory. And we will be covering this quite a bit throughout the remainder of these videos. So for right now, just notice here that this allows for us then to get the value that's actually stored there. And you'll also notice that I have a %d instead of a %p. Which brings us to the last part of our function. And that is the call our helper function, which essentially accepts a memory address and returns a memory address. And you'll see here that in this example, I am declaring another temporary variable, an int b that's going to store the value of our computation, and a pointer to an integer that is going to simply be used as a convenience variable to store the address of our int b. Now keep in mind that these variables right here have a scope only inside of this function. In other words, they do not have a lifespan outside of this function. Once this function is completed, then these variables essentially disappear. So we do our calculation. We then simply assign the address of int b to the value or the variable for the pointer, and we return the pointer variable. Shouldn't seem like there should be a problem, right? Well, if you come over here to the table, you'll see that everything starts off fine. Int a is still 0, FECC is the address, but you'll notice here that our int b, which was the value inside of our function, is not yet been initialized, so it is essentially garbage. And then we use this operation and assign the value to our int b. So in other words, we're simply saying the 0 that was passed, the variable that was passed by reference, or the address of our int underscore a4, we simply added 1 to it. So this essentially represents 0 plus 1, and we are now storing 1. Well, after we are done with the computation, then the value of our int a is still going to be 0, but the value of our int b is now 1, and the address of our int b stays the same. So in other words, this is this FE98. So you'll see here that it was FE98, FE98 for our int b, and the address for our int a stayed as FECC. So far, so good. Now, we return the address of our int b. We come back to our calling function and we complete our table. And so you'll see this is where we start to run into a problem. Our address of int a4 is still FECC, nothing's changed there. The int a4 pointer still holds the address of int underscore a4. Our value stored at our int underscore a4 underscore pointer is 0 because we didn't actually make any changes to the a4 variable inside of our function. But notice now here that the int b4 pointer is FE98, but look at the value that is stored at the int b4 pointer. Essentially, it's back to garbage. And essentially what this is saying is that a variable that is declared inside of a function cannot be passed by address out of the function, because once the function goes out of scope, you can't predict what that value will be anymore. And that was the reason why we wanted to go back to these earlier examples to note that essentially every time we called one of these functions, we were essentially reusing the memory. So it's very important to notice that memory inside of a function is going to be reused after the function completes. Now, we will look at this in a little bit more detail in future videos. I would like to take just one last second here to point out that you can actually run our V4 example separately if you would like to see it with a little less clutter. So in this case, we're simply going to run our V4, and you'll see the entire table and the entire progression of this example. And once again, I encourage you to take some time to really and truly understand what is going on here, because we will be using this in the future. So I hope you found this video useful. It was a little bit complicated, I know that, but if you have any questions or comments, don't hesitate to email me, and thank you for watching.